So in terms of velocity, position, and displacement, we can also translate the integration notion and see what the area below the curve means. Suppose that if you're driving like a straight highway and you have a position function as t for t bigger than 0, then if you're moving from position A to position B and you're going from left to right, we can check the change in this in position or the displacement as s of b minus s of a, and this is going to be a positive change. It's going to be a positive displacement when we're going in this direction. Now, in the opposite, if you're going to have that s of b is less than s of a, then you can have that the displacement is going to be negative. So in this scenario, with b being bigger than a and s of b being smaller than s of a, then you're going to have that the displacement is negative. So notice moving in this direction means a positive displacement, moving in this direction is a negative displacement. Now, if you assume that the velocity b of t is representing the velocity of the object of a particular time t, then we can have that b is the derivative of the position function. Now, this means that s is going to be an antiderivative of b. So you can think of it as the position being the antiderivative of the velocity. And from the fundamental calculus theorem, you're going to have that the integral from a to b of the speed is going to be the integral of a to b of s prime of t. And that's going to be s of b minus s of a. So essentially, you see that the integral of bt dt is the displacement or the change in the position between t equals a and t equals b. In an equivalent way, the displacement over the interval ab is going to be the net area under the velocity curve over ab. And if you have particular function b of t that has positive and negative areas, the integral is just going to be the net area, and that's going to measure the displacement as well. So in this scenario here, where we have a positive area a1 and a negative area a2, the displacement is a1 minus a2, and that's the total net area or the integral of ab of bt. Now we're talking about just displacement, so this is moving to the left and then moving to the right. And here we're moving to the left wherever it's positive, and then we move to the right where it's positive, and we move to the left where it's negative. But we can talk just about distance traveled. So essentially, the absolute value of the speed and the integral of the absolute value of the speed is going to give me how much distance is being traveled. Well, in displacement, you can move 5 units to the right, and then go back in 5 units to the left, and be on the position 0. On distance travel, that same movement is going to give me 10 units of movement. So in distance travel, we're always adding how much we move on the particular area. So let's see the definitions and the summary of this. For position, velocity, displacement, and distance, we have that the position of an object moving along the line at time t can be denoted by s of t, and is the location of the object relative to the origin. The velocity of an object b of t is going to be s prime of t, and by the fundamental calculus theorem, we can see that the displacement of the object between t equals a and t equals b is going to be s of b minus s of a, that is represented by the integral of a to b of the speed. Now the distance traveled by the object between those 2 points is going to be the integral, but from the absolute value of b of t, or the absolute value of b of t representing the speed of the object at the time. Now let's see an example of this in play. So we have that a jogger runs along a straight road with velocity in miles per hour, and the velocity is given by the function 2t squared minus at plus 6. And we're moving between the first 3 hours. So we're going from t moving between 0 and 3. Now we want to graph the velocity function over the interval 0 to 3. We want to determine when the jogger is moving in the positive direction and when it's moving in the negative direction. We also want to find the displacement of the jogger in miles on the time intervals 0 to 1, 1 to 3, and 0 to 3, and make an interpretation of these results. And finally, check the distance traveled over the interval 0 to 3. So for the first thing, notice that the function b of t is a quadratic function. We can factor this quadratic function though. We can take a 2 factor of it, and we're going to get with t squared minus 4t plus 3. That can be factored as twice t minus 1 by t minus 3. So notice that we have some important points at t equals 1 and t equals 3, where the velocity is going to become 0. These values are going to be the intercept on the graph of the function f, and they're going to be important points to split the domain. Now notice that this is a parabola function clearly, and because 2 is a positive number, then this is going to be facing up, opening upwards, another way to see it. Now the velocity on 0 to 1 means that the jogger is going to move in the positive direction. And let me see, we can check this very quick here on the board. So twice t minus 1, t minus 3. And remember that we care about the interval 0 to 3. So we can just do 0 to 3. But this is a split in 1. And so if we take a number between 0 and 1, let's say 0.5, this is going to be negative here and negative here. So this is going to be overall positive in this part. And when we take numbers between 1 and 3, let's say 2, this is positive, but this is negative. So this is going to be negative overall. Okay. In terms of what's going on, likely because of this being a parabola function, what is happening is that you have this kind of behavior going on. And so the area under the curve is of course going to be positive in all the intervals between 0 and 1. This is where the function is positive, so this is going to provide me with positive area. Now the function is negative from 1 to 3, so this is going to provide me with some negative area. And depending who is bigger, then we're going to have one displacement or the other. Now from doing the integral, we can calculate what the displacement is. So we can do s of 1 minus s of 0, and that's going to be the integral from 0 to 1 of the velocity function. We integrate here with our velocity function, and that's going to give me a positive result, which is going to be 8 over 3. So that's just the result on the positive area that we just described. Now, if we're going in total and we go for from 1 to 3, so now we're going from the negative area. This similar calculation gets me that I'm going to get minus 8 over 3. So pretty much this area that we're doing here is going to be the same thing that this area that we have over here. And in the total displacement from 0 to 3, that displacement is going to be 0. So that means that the jogger is going to return to the starting point after 3 hours. Now, from this, we can deduce that the total distance traveled by the jogger is just going to be twice a over 3, since we have a over 3 on the interval 0 to 1, and we have also a over 3 on the interval 1 to 3. So the distance traveled in total is going to be 16 over 3. Alternatively, we can just do the integral and find the same result. So we're going to do the 0 to 3 integral of b to absolute value of b of t. That's going to give me a split between 0 to 1 and 1 to 3. And this part the function is positive, so it stays the same. And this part the function is negative, so we multiply by a minus. And once that we do the integrals, we're going to get that this is 16 over 3. Okay, so this is the first example of whatever we can do with application of integration. Now we can see graphically how this is occurring here in a better detail. You can see the positive area going on in here, the negative area, and if we consider the absolute value to check on the speed, then we can see that this is the total distance traveled, where we add up all this to summarize the integral. Now, given that we have now considered that the displacement can be observed from the velocity and from the fundamental calculus theorem for a couple points, then now we can define a function position from the velocity function. So with the fundamental calculus theorem, we can take the integral from 0 to t, where t is certain time that we don't know yet, and we're taking the displacement over the interval 0 to t. We're gonna give the initial position, and with that we have enough to determine what is the general position at certain time t. But we're going to see more of this in part 2 of this section.